All right, this is lesson 3.03. This has to do with graphing rational functions, and there's some rules for that, and there's six steps to graphing a rational function. So I'm going to go over the rules real quickly, and then they may not make a lot of sense while I'm just reading over them, but then we'll apply them and they'll make more sense to some problems. So the first is finding a vertical asymptote. So if we just draw a couple of axes here, like that, a vertical asymptote is a line that the graph cannot touch or go through. And so, for example, right here, if I drew, I'm just making up one right now, we'll learn how to calculate them. If I draw that line right there, and that's at x equals 3, then it means a graph can come close to that line, but it can't touch it. Or on this side, it could come close to that line, but it can't touch it. So that's a vertical asymptote. Vertical means up and down. Now, a couple of the rules here. So the vertical asymptotes are the values of x that make the denominator go to 0. So it's kind of what we did. It's exactly what we did when we talked about zeros and roots a couple of weeks ago. Now, holes exist for zeros of factors that cancel. So let's take this as an example. So we have a couple of factored polynomials here. So the two values that the denominator can't have here are 3, because 3 will make this go to 0, and 2, because 2 will make this go to 0. So 3 and 2. But there's a difference. You can see that the x minus 2 term will cancel. Remember, we talked about how you had to get what the excluded values, these are excluded values, were before you canceled. And so in this case, we got the 3 here and the 2 here, and then after we got that 2 out, we then canceled this. And your final answer would be left only with x plus 1 over x minus 3. But if you just looked at that, you wouldn't know that 2 is an excluded value. So it's clearly different in some ways than the 3 is here. And here's what it is. The 3 is a vertical asymptote. It's basically like what I wrote right there. That would be the 3. The 2, on the other hand, is a hole. And let me illustrate what a hole is just with a straight line. So I'm kind of expanding this. So a hole it's on a line, or on it could be a curve as well, but it's a single point where that curve or that line can't exist. So this is a straight line. It's just one continuous line, except it has what's called a discontinuity there. It means that that line does not exist at that single point, and that's called a hole. So the 2, whenever you have a factor like this that cancels out, and the 0 in it, the one that the value of x that makes it go to 0, in this case is 2, the 2 is a hole. If it's a canceled value, it's a hole. If it's not a canceled value, like x minus 3, so the 3 is not canceled out, that would be a vertical asymptote. Okay? Next, horizontal asymptotes. So horizontal asymptotes, if I use this same graph here, are asymptotes, and you draw them with dashed lines always, that go in the horizontal direction like that. Okay? Again, it's a line that the graph can't touch. All right? So that would be horizontal. Now, how do you tell them? Now, the rules for horizontal asymptotes are a little more involved, so let's go through them. Okay, so horizontal asymptote. If y equals 0, if the horizontal asymptote is y equals 0, if the degree of the denominator in expanded form is greater than the degree of the numerator. So, in other words, y equals 0 would mean it's right on the x-axis. If I went back to this example up here, it's right along the x-axis here. Okay, that would be y equals 0. So when does it do that? It does that when the degree of the denominator, so degree is the highest exponent, the largest exponent, okay? That's called the order or the degree. So here the degree is 2, because the largest exponent you see on the bottom is 2. Up here it's 1, even though you don't write it, it means that the exponent for that x is 1. So since the degree is larger in the denominator than in the numerator, then that means that the horizontal asymptote, if you come back here, is going to be right along the right along the x-axis. It just runs right along the x-axis. It's at y equals 0. Okay, next, It does not exist at all. You don't even have one if the degree in the numerator is greater than the degree in the denominator. So in this case, you don't have a horizontal asymptote at all, because x to the third degree right there is greater than the first degree right there. So this number is greater than the one that's there, and therefore you don't have one. What you do have, however, something called a slant or oblique asymptote, but we're not going to deal with those. Okay, we were told not to deal with those. Okay, finally, C. If the degrees in the numerator and denominator are the same, then the numerator coefficient over the denominator coefficient is the horizontal asymptote. So here you have an x to the first power, and down here you have an x to the first power. So the degree is the same. So what you would do, let's just read this. The degree of the numerator is 1, is the same as the denominator 1. So the horizontal asymptote is 3 over 1. In other words, this coefficient over this coefficient, you can go ahead and write the 1 in there, it's 3 over 1. And that's going to be the horizontal asymptote. So it means it's going to be at x equals 3, which is right about where I drew this one right here. It's 1, 2, 3. It's right about where I drew that one right there. Okay? That one's a little more involved. But again, we'll practice these. We'll go through these and look at these rules as we go through them. We do the problems. Okay, let me talk a little more about the slant or oblique asymptote. If the degree of the numerator is greater than the degree of the denominator, we said there's no horizontal asymptote, but there is a slant or oblique asymptote. So again, it's like this over here. Then A, no horizontal asymptote exists, and B, a slant oblique asymptote exists that is equal to the numerator divided by the denominator. In other words, you've got to do a synthetic division on this, or a long division, whatever you choose. But do a synthetic division, you'll come out with a quotient, with an answer. That answer is the oblique or slant asymptote. So if I use synthetic division and on this problem, if I did it on this problem, the quotient will be the slant asymptote. Here it would be x minus 3. So if I divided x into 5, let's just go ahead and do it real quick. So x minus 5, so it's going to be minus 5. And I'm just going to quickly do the synthetic division. This coefficient is 1, this one is 2, this one's negative 3. We bring down the 1 to there. Negative 5 times 1 is negative 5. 2 minus 5 is negative 3. Okay. Negative 5, negative 3 is positive 15. This gives us 12. Remember, this last one is the remainder. We don't care about that. You ignore that. You just look at the 1 and the negative 3, so it's going to be x minus 3. Since this was an x squared, this is going to be an x. There's the answer if you did the division and ignored the remainder. So that is actually going to be the slant asymptote. And if you plotted that for x equals 1, if x equals 0, this would equal negative 3. If x equals 1, this would equal negative 2. If x equaled 3, this would equal 0. And so you could just plot that line. And what you're going to end up with is a slope line. That's why it's called a slant asymptote. Okay, we're not going to deal with those in this lesson today, though. But that's how you do them. Okay, finding the y-intercept. To find the y-intercept, you just set all the x's to 0. So if I take this and I set x equal to 0 here and here, I get 0 plus 1 is 1, 0 plus 5 is 5, 1 over 5 is 1/5. So the y-intercept for this graph, for this particular graph, would be at 1/5 on the y-axis. So let me just draw again another little axis, a set of axes here. So y equals 1/5. If this is 1, it would be right there. It would be just above 0 if that represented 1. Probably even closer to the line than this, okay? Okay, finally the x-intercept. How do we get that? We do that by doing just the opposite. We set y equals to 0. So over here we would set y equal to 0 and figure out what x is. That sounds like it might be hard, but it's not. Let's do it over here. 0 equals x plus 1 over x plus 5. Okay, now that's not hard to solve. We're going to take x plus 5, we're going to multiply the top of both sides by x plus 5. That's legal. You can do anything to an equation as long as you do the same thing to both sides. Okay, so x plus 5 cancels with x plus 5. That was easy. And 0 times x plus 5 is just 0. It doesn't change. 0 times that is that. So that equals 0 equals x plus 1. And therefore x would have to be equal negative 1. Okay, so the X-Intercept would be -1, so that means if I would go back here, I go to right about there, and that would be -1 right there. Okay, that's where it would intercept the x-axis. Finally, if you want to complete a graph, and we'll do that, then you pick 2 or 3 points to the left of the horizontal asymptote. So let me just come back to this graph as an example. So I'll just say I said horizontal. I meant to say vertical asymptote. I'm going to just draw a vertical asymptote there. I want to pick 2 or 3 points on this side of it, 2 or 3 x values, so I already have, I could pick a couple over there, and I can pick a couple over there. And with a little experience, all you need is about 2 to figure out what the actual graph is going to look like. So we'll do that as the last step, and then really that's the second to last step. Once we've done all 6 of those steps, except we're not going to do slant asymptotes, we'll go to Desmos and we'll see how it looks. Did we come pretty close to graphing it accurately? Okay? All right, so here goes. We're going to do the first 3 problems on this, and that is all. If you want to come to tutoring, I can do others with you if you would like to do that. Okay, so here we go. So one thing you're going to have to do is have your function in both expanded form and in factored form. Well, this is expanded form. There's not much to making it in factored form except to do this. I'm going to factor out the 3 on the top. Okay? And there that is. So that's factored form. So this is expanded. This is the way it came originally. And this is factored. I factored everything that I could, and there wasn't much, only that 3. Okay, so to find the vertical asymptote, I'm going to abbreviate that VA. This first one, I'll just draw an arrow to show you what I'm referring to. I'm referring to vertical asymptote. What that simply is anything that makes the denominator go to 0 and doesn't cancel out by the end of the problem. Well, we can see, so you have to go to the factored form to do that. So we see that -1 is going to make this go to 0. So vertical asymptote is at -1. And since the x plus 1 doesn't cancel, if there was an x plus 1 on the top it would, but it doesn't, then that means it's a vertical asymptote. And since there is nothing on the bottom that does cancel, like the example that I gave you here, where the x minus 2 over x minus 2 canceled out, that's when you have a hole. But we don't have any factors on the bottom here that cancel, so you can go ahead over here on the side and just write no holes. There are no holes in this graph. All right, let's go ahead now and do the next one. That's horizontal asymptotes. So remember, there's 3 possibilities with horizontal asymptotes. You just want to identify which one you're dealing with. Is the degree of the denominator greater than the degree of the numerator? Is the degree of the numerator greater than the degree of the denominator? That's case B. Or are they both the same? The degree of the numerator and the degree of the denominator the same. Again, degree means the exponent on the largest exponent that you see. So up here the largest exponent is on the bottom, here the largest exponent is on the top, and here they're both the same. Okay, so we look at this one, and now you have to go back to expanded form, okay, to do this, the horizontal asymptote. Okay, so HA is this guy right here, horizontal asymptote. That's the one that's going to go sideways. And I'll plot them here in just a second. Let's do horizontal first. Okay, so here we go. This is a 3x to the first, and this is an x to the first. So they both have an exponent of 1. That means the degree is the same. So what you do then is you take the coefficients, and I'll go ahead and write a coefficient there of 1. So you have a coefficient of 3 over a coefficient of 1. So you have a horizontal asymptote at 3. So let's go ahead and find out where those are. Vertical asymptotes go at like this, and what it means is it's at x minus 1. Let me be more specific. X equals minus 1. It's at x minus 1. So that's right here on this graph. So I'm going to come here and write it at, this is vertical. It's going up and down at x equals -1. I'm going to just draw a dashed line. That means the graph cannot touch or cross over that line right there. Okay? And for the horizontal, I have 3. That's the one that's going to go sideways. So I go up the x-axis, 1, 2, 3, right there. Okay, so there's vertical and horizontal asymptotes. So our graphs cannot touch either one of those lines or cross over either one of those lines. Okay, next we're going to go on to number 3. We skip it, slant asymptote. Number 4, find the y-intercept by setting x to 0. So we're going to take this function right here, and we're going to say this is the y-intercept. I'll just write y-int. So over here I'm going to write y equals, and I'm going to take this equation, just plug in 0 wherever I see an x. So 3 times 0. Okay, 3 times 0 is 0, plus 6 is 6. 0 plus 1 is 1. So that equals 6. So the y-intercept is going to be at 6. So where is that? You go up on the y-axis, 1, 2, 3, 4, 5, 6. I'm going to make a big old dot right there. That's the y-intercept. Okay? Now the x-intercept. And that's going to be where y equals 0 and you figure out what x is. So 0, and now we just put this equation here. Okay, so there you go. So now how do we do this? Again, it seems complicated. It's not. Let me erase this because it's kind of in the way of where I'm going to want to write. So x-intercept is what we're looking for. I'll write it up a little higher here. Okay, so what we do is what I said before. You just multiply the top of this side by x plus 1, and you multiply the top of this side by x plus 1. This cancels with this. And 0 times this is just 0. So you end up with 0 equals 3x plus 6. Subtract 6 from both sides and divide by 3. I trust, well, let me just do it. Some of you may not remember how to do your algebra there. So it's going to be negative 6 equals 3x. Divide both sides by 3 now. Cancel, and you end up with x equals negative 2. Okay, so the x-intercept is going to be at negative 2. So I'm going to go back 1, 2. It's right there. Okay. Now one thing you'll notice about this is one of these dots is on the right side of this vertical asymptote and one is on the left. And the line cannot cross over. That means there's two different parts to this graph, and one of them is going to go through this point right here, and one of them is going to go through this point. Okay, so where are we? So now let's go ahead and let's pick 2 points to the right of the vertical asymptote, which is x, which is -1, and 2 points to the right. Now I'm going to do the math in my head. You do it on a calculator, but I'm going to pick the points. I'll go down here. I'll go over here. I'll do it over here so you can see it better. And you get to pick whatever points you want. You don't want to make them too far away from that. So it's at -1. I already have 1 point at x equals 0, y equals 6. I'm going to pick 2 more. I'm going to pick x equals 1 and x equals 2. I already have x equals 0. I can write that here. 0 goes to y. This is x, and this is y, but instead of calling it y, they call it f of x. That's called function notation. I'll write y above it because I always think of it as being y. Okay, so 1 and 2, and then let's go to the left of the vertical asymptote. So we already have 1 right there at -2, 0. So we know that one. But I'm going to pick 2 more. I'm going to pick -3 and -4. Okay, and I'm going to kind of do these in my head. Okay, you do them on a calculator. So if I put a 1 in here, I get 3 times 1 is 3 plus 6 is 9. 1 plus 1 is 2, so I have 9 over 2. That's 4.5. I'll write it in fraction form. I could write 4.5. Okay, how about 2? 2 times 3 is 6 plus 6 is 12. And 2 plus 1 is 3. 12 over 3 is 4. Okay. Okay, how about -3? 3 times -3 is -9 plus 6 is -3. and negative 3 plus 1 is negative 2. So negative 3 over negative 2 is positive 1.5. You can do this on a calculator. I don't expect you to do this in your head. Finally, 4. Let me draw some lines like this that we should have separated here. 4. Okay, 3 times negative 4 is negative 12, plus 6 is negative 6. And negative 4 minus, or plus 1 is negative 3. So negative 6 over negative 3 is positive 2. Okay, so let's plot these two first, 1 and 2. So 1 goes to 4.5. 1, 2, 3, 4.5 is right there. And 2 goes to 4. 1, 2, 3, 4. Right there. So I have 3 points. 1, 2, 3. I know that they can't touch, and this is a curve. I know they can't touch this dashed line or this dashed line. It's a little hard to see the dashed lines, but I think you can see it. But what that means is this one's going to look like this. Along the asymptote, it's going to go up to negative infinity and get closer and closer to that asymptote as it keeps going up. For this one, it's going to come down and curve through this, and it's never going to touch this dashed line right here, and it's going to keep coming along. Well, I drew it touching, but I shouldn't have. It's going to go further and further out and never touch that dashed line right there. So it's going to curve like this. Okay, next up, we have negative 3, 1.5. So I go 1, 2, 3, and positive 1.5 is right there. And I go negative 4. 1, 2, 3, 4, and I'm up 2 right there. Again, we have 3 dots. We have a dashed line right there that it can't touch, and a dashed line right there that it can't touch. So it's going to do this. Remember, these are always going to be curves. They're never going to be straight lines. They're almost never. So there you go. That's what the graph would look like. Okay? So what I'm going to do is I'm going to move over to Desmos, and I'm going to type in this equation. So let's make some key points here. This was at negative 2 right here. That's the X-intercept, and the Y-intercept was at 0, 6. I should call this negative 2, 0. That's the X-intercept there. There's 0, 6 is the Y-intercept. Okay, so let's go to Desmos for a second. Oh, okay, and all right, so I went ahead and put the equation into Desmos here, and you can see it looks like the graph that we plotted there. You can find some intercepts here. Those gray points are intercepts. So there's the Y-intercept at 6, 0, 6, what we said. And here's the X-intercept at negative 2, 0. That's what we said. And each of these along the X-axis each square represents 1. So if I go back here, I'm at negative 1. You'll notice that the curve never touches the line at X equals negative 1, where I'm tracing the cursor up and down right here. That is our vertical asymptote. Okay, and we said the horizontal asymptote is at 3. So on the vertical axis, let's see, 1, 2, and 3. So everywhere I'm tracing, I know it looks like it's about to touch, but it's not. Everywhere I'm tracing, the lines will not touch that line at y equals 3. Even though it's getting very, very close, it'll actually never, ever, ever touch that line. That's the horizontal asymptote. All right? So, and there's no holes in this. Desmos doesn't show holes, by the way. So there's no holes. So this looks like what the graph is that we had, which I'll flip back to that. And there it is. Okay, so that's pretty close to what we have over on Desmos. All right? Okay. All right, now we're moving on to number 2. All right, so here we go. This is expanded form. We're gonna factor it. There's not much to factor out on this one either. So we're gonna do that. We're gonna pull the negative 2 out. So 2, negative 2, and then inside the parentheses x plus 4. Okay, so negative 2x minus 8 is negative 2 outside the parentheses times x plus 4 would give you negative 8. So there's the factored form. Okay, so vertical asymptote is simply what makes this go to 0, and it would be that negative 4. Negative 4 plus 4 would be 0, so that's going to equal negative 4. Okay? So I'm going to go back 1, 2, 3, 4 to this point right here. and I'm going to draw the dashed line up and down. So the graph is not going to be allowed to touch that dashed line. So there it is. There's the vertical asymptote. Horizontal asymptote. So what I want to ask myself is, now you have to go back. Vertical, you had to use this one. Horizontal, you use this one. What is the power? Which one has the greater power? The one on the top or the one on the bottom? Well, this is x to the first, and this is x to the first. So the rules say, we'll go back to our rules, that if the degrees of the numerator and denominator are the same, then the numerator coefficient over the denominator coefficient is the horizontal asymptote. Okay, so the degrees are the same. They're both to the first power. So you have a 1 up here, although you don't write it. So it's 1 over -2. So that's going to equal -1/2. Again, 1 there, a -2 there, so it's -1/2. So that means if I go here and I go down just half right there, I'm going to draw a little dot so I don't cover up everything. It's going to be a dashed line through that dot right there. Should do this with a really sharp pencil so it will clearly show halfway between. So it's halfway right in there. It should actually be exactly halfway between these two lines right there. Okay, close enough. All right, that's the horizontal asymptote. So the graph cannot go through that line either. So you have two lines that it cannot go through. All right, next up, we're not doing, if there's a horizontal, there's not a slant asymptote, and we're not doing slant anyway. So let's go on to X-Intercept, or Y-Intercept actually. So that's where you set x equal to 0. So y equals, I'm just going to use this function right here, 0 minus 2 over -2x minus 8, or -2 times 0 minus 8. Okay, so on the top, 0 minus 2 is -2. -2 times 0 is 0 minus 8 is over -8. So that's going to equal positive 1/4. So right here it means I'm going to go up 1/4. I'm just barely above the x-axis, okay? It's right there. If I draw too big a dot, it'll take up too much space. It's right above the x-axis. It's at 1/4 above. All right, and the x-intercept, that's where you set y to 0, and then you figure out what x is. And I did it again. I wrote this right in the way of where I'm going to need to write. X-intercept. Okay, and that's going to be equal to okay, so how do we solve that? We just multiply the top by what's in the denominator there on both sides. Okay, this cancels with this, and 0 times this is 0, so it becomes 0 equals just that. So that's going to be x equals 2. And that's right here. Okay, so let's go ahead now and pick 2 points to the right and 2 points to the left. You want to kind of pick them strategically. So the vertical asymptote is right there. It's going up and down. So if I look right here, I already have 2 points to the right of this line. Let me pick one that's a little closer. This line is at -4. I'm going to pick a point at -3. I want to see where that point lands along here. That'll help me determine what this curve is going to look like better. So I'm going to pick -3. I already have one here. I have at x equals 0, y equals 1/4. Okay, that's what we figured out, the y-intercept. And at x equals 2, y equals 0. That's the x-intercept. So I have a couple of points already. So I'm going to do -3 here, and then I need 2 points on the left side. I don't have any points on the left side of this line right here. So it's at -4. I'm going to pick -5 and -6. That sounds logical. Okay, so let's do -3. And I'm just going to do this in my head. -3 minus 2 is -5. And negative 2 times negative 3 is positive 6 minus 8 is negative 2. So I have negative 5 over negative 2. That's positive 2.5. So if I come back here, I go up 1, 2.5 right there. Okay, again, do that on a calculator. Don't try to do it in your head. Sometimes I make mistakes doing it that way too. Okay, in fact, I want to check my work. Negative 5, positive 6 minus 8 is negative 2. Negative 5 over negative 2 is positive 5 halves, which is 2.5. So now I can see a curve here. And I know it can't touch this line, and I know it can't touch this horizontal asymptote, so I'm going to sketch it as best I can. It's going to come down. It goes up to infinity, but when it comes down here, and it curves, and it curves, and it goes along that dashed line, but never touches it. So there's one of my curves. All right, the other one we said is going to be at negative 5, so negative 4, negative 5 is right here on the x-axis, so let's plug that in. Negative 5 minus 2 is negative 7. Negative 5 times negative 2 is positive 10 minus 8 is positive 2, so it's negative 7 over positive 2. That's going to be negative 3.5. So if I come back here, I'm going to go down 1, 2, 3.5 right there. Negative 6, I go back here. So negative 6 minus 2 is negative 8, and negative 6 times negative 2 is 12 minus 8 is 4. So negative 8 over positive 4 is negative 2. So I'm going to come back 1, 2 here, and I'm going to go down 1, 2 right there. Now with 2 points, how do you really determine a curve? Well, first of all, you know it's a curve. You know that as it goes up towards this asymptote here, it's going to go off towards infinity like that. As it comes down to this asymptote, it's going to go closer and closer and go to negative infinity there. So you just fill in this little slot right here with a curve, and there you go. Okay, so that's what it looks like. It's fairly similar to the first one that we did. Okay, what did I say that was? Negative. I said it was negative 2, right? Okay. All right. So let's go to Desmos. Let's see how that works. Okay, so in Desmos, I went ahead and put the function in. I wrote it wrong, though. Let me change that. It was x minus 2 over negative 2x minus 8. I always put things in parentheses in Desmos so I don't run into any PEMDAS problems with something doing an operation before it was supposed to. Okay, so let's come down here. We had a vertical asymptote at negative 4, and here's negative 4 right there on the x-axis. So if you go up and down where I'm tracing the cursor, those two curves are never going to touch that line, even though they'll get really, really, really close. Okay? I have a horizontal asymptote of negative 1/2. It's really hard to see that one, but it's right. You can see. Here's 1/2, negative 1/2 on the y-axis. So if I go back and forth, you can see the line is not touching. It's not going to ever touch that line at negative 1/2. All right, the y and x-intercepts are the gray dots. So right there, I have a y-intercept at 1/4, and that's what we calculated. And I have an x-intercept at 2, and that's what we calculated for that as well. And so you can see that our graph looks pretty much like the one that we sketched back there. At number 2, in class for period 3, I did number 3 as well. Kind of quickly though, I'm going to leave it at this. I am still having some computer issues with the ability to make these videos, and I'm afraid this is going to crash on me in a second. So we'll leave it at 1 and 2. That's all you're responsible for, okay? And that's it. So finish this up and turn it in ideally by Saturday for period 3, Monday for period 1 in class. And that's it. We'll see you in class next time. Bye-bye.